And I hope that you can all see the main slides. Yes. Can you confirm? Can I see some thumbs up? Excellent. Thank you so much.
Great, Marine.
Yeah, thank you. Okay. So this is pulling out of a class that I teach in the fall on machine learning, but is really motivating by the seemingly consensus that scientists are in a reproducibility crisis. And I don't want to be too dramatic about this. And so what I like to think about is we have reproducibility problems, but I like about the study I'm showing you is that we can quantify it. I have my own example where I submitted a paper with a student and I did not know how to learn Python. And as the revisions came and I tried to modify the code and I realized there was a bug because actually I did not reproduce the study before we submitted it. And so since then, about like in 2019, in my research group, we are putting a lot of emphasis on reproducing our own results before we even submit papers. So let me show you this study by Monia Baker. This came out in Nature, so you can believe it or not. But this was a nice summary of a survey that they did to a wide range of scientists about what people thought about whether or not we had a reproducibility crisis to motivate this, improvements from us. So according to that survey, which I think had 1,500 scientists, 52% of the surveyed people said that they really thought there was a significant reproducibility crisis. And then 38% said there was a slight crisis. These vary by fields, which I think is kind of interesting culturally as we think about scientific culture. But out of that survey, this plot is actually showing you according to different fields. We have chemistry, physics and engineering, earth and environments. We're more into this area, biology, medicine, and everybody else. So the y-axis is showing you the percent of published literature that is reproducible and how we feel about it. How much, what is our confidence about that? And you can see the chemists are actually quite confident that they can reproduce what is in the literature. And that tends to decline as we go on this x-axis. So physics and engineering is also quite confident. The earth environment, we tend to be a little bit split whether or not we can reproduce work or not. And then as we go to a maybe more complex system, people are less and less confident about reproducibility. But I just want to say, like from the first slide where we talk about there is a significant crisis to this actual level of confidence, I think it's still debated on what we think about what reproducibility actually means and what we can actually indeed reproduce. So I wanted to just pull out the idea from the geosciences. So, excuse me. In this plot you see on the right, what I think is quite interesting is at the researcher level, have you failed to reproduce an experiment? And for us, it might be, have you failed to reproduce the results of your paper, of your full stack paper? And it's interesting to see that, chemistry thinks that they cannot reproduce others' research. But what we're really starting from that result is really look at how much of your own research you cannot reproduce. And that number is, to me, a little bit more worrisome. In the earth and environment, we're a little bit more confident compared to other research fields. But I'd like to know that there's still 40% of researchers that claim that they could not reproduce their own results. And so that is something that we should at least be able to control. And then another number that I think is still worrisome is 60% of the published results may not be reproducible. And I think we should be able to tackle this problem by improving the way we work. It's just learning about new habits and demonstrating and proving that we should be able to reproduce one's work. In part because the type of data we use is as it is, we just use it. We all use the same data, so we should be able to reproduce the same thing. It's not like we go in the lab and make new data. We actually pull it out of seismometers in the most cases. So that this is, to me, a little bit of something that I think we should tackle as a community. The good thing about open science in general is I found the community very positive and optimistic about how we can tackle this. And so you would actually find in the literature about open source software, open science, that there's a lot of optimism and recommendations on how to do it. And there's no shaming about, when to start, what are the steps to do. I think it's a very positive way that we can work forward. So in this paper on reproducibility that I pulled out, and I really liked it, the main big picture message they say is there are many small, simple steps that we can take to improve the reproducibility. And so we're not claiming to make it full stack, completely reproducible. What I think the field is going toward is recommending small ways that you can just improve on your daily life to slowly build up this skill set to become reproducible. Just a few more slides on this topic. I really like this quote from John Claerbout. So I was at Stanford and I saw him in the hallway. But he wrote in 1992 that the actual scholarship, is, get there, the full software environment, code, and data that produce the results. And so what's interesting in there, it's, you can see all these words of software environment, we have the code, we also have the data, and we produce the results. And so we want to think about, what is reproducibility? It has several components that we'll go through in this lecture that defines really what is the full reproducibility. Is this extra work? It is at the beginning, a ton more work. Talk to my group members. In the short run, learning these skills in the full range of skill is actually very time consuming. However, in the long run, by learning these good skills, you actually accelerate your pipelines, you accelerate the way you work, you're more efficient forward. Why is it worth it? It really improves work habits and improves the quality of your work. And by that, we can mean maybe people will check your codes, and that is good to have others' eyes on your set of codes. I see bugs in my own all the time. It improves teamwork because it makes us work as a team, and everybody has ways to contribute that is unique. Everybody can contribute to a piece of the software. And the way that we have to work together is a very important skill for the professional settings, for the academic setting. And so just in a single research investigation, learning how to work as a team is very important, especially as we move toward a frontier in our research that is more interdisciplinary. Like, we have to learn how to work together on the kind of nuts and bolts of research. It gives a greater impact. One thing that we can do is we can be less competitive. And if somebody has done a piece of code and put it on GitHub, then the idea is already out there, but it's already owned or it's proposed by somebody. So in a way, you don't have a set of competitive teams, because once you put your idea there and it's open, then you've already claimed it in a way. So in a way, like, I put out ideas on my group, you can see it, and it's a little bit too open maybe, but the advantage of that is, people know what we're working on. So you also don't have to double task. We also need to improve, but I think it would be nice to get more citations and licensing once you make all your code out there. Another thing that I, as a still junior faculty, is that I found that establishing this reproducibility in our research is allowing me and others to become more effective and really better at training and advising students. This is a long run. It's taking me a couple of years to get there, but I found that it is true. We've been able to onboard undergraduate students to do graduate level research because we have developed this kind of pipeline on running people with good, with better tools. And one thing that in this paper and others they talk about is research is a public good. It's public funds that pay for the research, and everybody should be able to access it. So another thing about what the definition of reproducible science is that when anyone, including others or oneself, can understand and replicate this step of analysis and apply it to the same or even data. So we'll spell it out a little bit about all of these replication and understanding what that means. We need to improve transparency in the data collection. processing and analysis methods, and the derivation of the outcome. So we can think about, in the data mining bits of our workshop, you'll think about, how do I download data? What are the exact processing steps? Tell me about the window length, sampling rate, frequency, and detail all of this workflow so then it can be reproduced. We often, as seismologists, I think, use publicly available data. And a lot of our processing methods tend to be or are becoming more and more open science. So I think in seismology, we're definitely improving on that. Transparency in communicating the results is important for reproducible science. And I think when we talk about communicating the results, we mean publication, tutorials online, presentations at conferences. And that might mean that we need to actually communicate all of the steps and the workflow of our results in the paper so people can actually reproduce it. That's one step. So let's break down a little bit of these terms of in reproducibility. And I'm extracting some of these slides, I should say, from the Turingway, which is a fantastic book about open science, reproducible workflows, and really nice way to cast and develop new projects as teams. So they explain what reproducible means. It is the same analysis steps performed on the same data set, consistently producing the same answer. Now, it can be a buggy code, but if you can reproduce every step from the same data to the final results, you should be able to reproduce it. And so this is an example would be, we're submitting a paper about ambient earth crust correlation, and we're trying to measure changes in seismic velocities. We download data, we process it, we cross correlate it, we measure DV in fixed parameters, and then we produce plots. The full stack of that can be packaged, so then we can reproduce it. And I have an example of a former postdoc, Kurama Kubo, who's reproduced exactly the same result on a different machine, but same workflow, same plots. And that is purely reproducible. That said, it's not the ideal grail because you can reproduce bugs and incorrectness, exactly. And so there's other way that we should think about this. For instance, on the same data, if you use a different piece of software and workflow, but it's doing kind of the same thing like ambient noise monitoring, but instead of using Python, I'm using Julia. So the analysis is slightly different, but I get to the same answer. So you can qualify this as a robust result when you have different methods to get to the same answer with the same data. Now let's look on the right here. Now we're going to talk about what if I use the same method, but somewhere else, like California, applying to the Pacific Northwest. And I find, let's say my result is about, I found that seismic velocities are correlated or anti-correlated with groundwater levels. This is my science results. I find that in California. Do I find the same thing in the Pacific Northwest? Maybe, maybe not. And if I can demonstrate that, I'm replicating the results somewhere else. And so it proves mostly like the science investigation is replicable in other settings. So maybe the underlying physical processes are well demonstrated. And then finally, generalizability. This is more on this can lead to understanding more the issue with machine learning models today, is the idea that I can rewrite the full code in different methods and different language, and I can apply it to a different data set and I get the same results. And this is the grail eventually what you say, taking the example of ambient earth crust correlation and seismic velocity monitoring. I have a code in Python and I apply it in California. Now I want to have a code in the computing language Julia, which I'm a big fan, and I do it in the Pacific Northwest, and I find the same results. So I demonstrate there that the method is correct and it gets to the same results, and the underlying physical process is also common and therefore must be kind of true. And so this is the grail. We talk a lot about reproducibility. This is just to make sure that we are correct. It's not to demonstrate how good, robust, replicable, generalizable a result is. It's just to make sure that we are doing the job that we said we did. So it's only like the minimal, that's the minimal units, I think, to correct science, not even good science. Scientific journals are slowly encouraging or requiring reproducible research. One of the early journals that talked about us was Biostats. And here are their statements, and they talk about reproducible research policies for papers in the journal to be marked D, freely available, so they have different rankings. Data and codes are published electronically to the journal's website in supplementary material. Code availability statement, which now you see in the AGU journals. Authors are strongly encouraged, not required, but encouraged to submit codes supporting their publications. And here are some platforms that you can do that, which we'll talk in a bit. Okay, so it's not yet mandated by all journals, but there's definitely a trend toward it. So this is why the community has no choice in starting to tackle this reproducible research if you want to keep publishing. That said, I do want to say that we should not be blind about reproducibility because we can still reproduce bugs. And so we should still work towards having robust codes, at least workflows and replicable. Okay, open science is a general statement of talking about what it tackles a little bit. So we have open data and software, which we understand, open access literature, which we'll get to, public participation. So like really we can, since we have open access to the public can actually talk to us, accessibility of scientific progress. You can see on the right, it's casted also as empowering infrastructure and the impact of the measurements, because we can actually spread the love of science further. Some definition about open science, there's actually a solid research field on the topic. And so this review is quite interesting from Vicente Saez in 2018. So they define open science as a transparent and accessible knowledge that is shared and developed through collaborating network. And the word knowledge in that review paper is quite defined. They pay some attention to this. They say it's an umbrella term used by the authors to explain what it is: code, data, scientific outputs, results, and publication, information and ideas. All of that is what is knowledge. The difference between it is open science knowledge, excuse me. The difference between knowledge in general and open science knowledge is the implication of transparency, accessible, shared, and collaborative developed. And this is where it stands out really, is what is open science is having this transparency and accessibility of the ideas. And so open scholarship in general can be seen in different ways. We have data, software, hardware with Binder, open access with the journals, open notebooks. This is talking about workflows. And then we have all this educational and outreach and inclusion that comes along this overall open scholarship. So it really means that everyone is welcome without discrimination of any sort. Okay, so I'll talk about the bits. Open data is documenting and sharing research data, and we'll talk about what that means for when we make data products. Open source software, we'll have a session about that in a little bit. So documenting research codes. Open hardware, it's documenting design, materials, and other relevant information about the hardware. We may not talk too much about this piece, but something that you may take out of this is sometimes if you report compute time in running your codes, you may say like the type of CPU that was used for that or the type of instance. And that is information that then can be used to reproduce, for instance, the compute time that you reported. And open access, we'll have a discussion by Alice about open access journals. Open scholarship for education, this is what we're trying to work on today. These are the bits that we are trying to promote with having open access teaching materials on the topic, making these virtual workshops, having an eye on diversity among the participants that we selected. This is something that I think all of us in general are working on. Open data. So let's talk a little bit about what are the recommended guidelines to promote open data from our own research. First, we need to consider that we should protect our raw data and not modify it. So it may be a little bit simple when we think about extracting data from seismometers, but what the archives, national archives do, like the the DMC, or now the Earthscope data services, is they have the raw data by itself. And that is nice to have, it's important to have an archive where the data is untouched, because every step of the workflow we come after is modification of the data and will come as part of the research software. The data should be available online, free access, on a reliable archive. So it's hard to have like FTP data shared among institutions, and under an open license, which can actually be used. The data in data products should be easy to understand. This comes with having data formats, metadata information, documentation to be machine readable and human readable. That means that you can read it with open source software, and you can also open the file maybe and have sufficient documentation on how to read the file and extract the information. Recommends to make your data easy to use, and really strongly recommend having standard data formats, even though they may not be the most performant format like HDF5. If it's standard, everybody should be able to access it. And then finally, make your data citable. So when we have data products like time series of changes in velocities, going back to my focus, we can actually publish our data sets and get a DOI for those who would like to reuse it afterwards. You can store your code and data on a range set of platforms. Maybe some of you are the most familiar with Zenodo. And Zenodo is a way it's integrated with GitHub, so you can do your coding, but it's a way you can upload up to 50 gigs for files for free. And it's pretty versatile. It's got some nice API to be downloading from Python, for instance. You can store a lot of data provided that each file is less than 50 gigs. So it has been, from my perspective, the most useful. But these are the ones that are quite good for large data sets, so Dryads. It's been quite, according to their website, you can host significantly larger data sets, so up to 300 gigs, some restriction on file size. It is curated by librarians. That means that librarians are looking at the data that you actually put in, check the metadata, and make sure that is actually conform and readable. And so you may pay a fee for the service of polishing your data. So it's kind of nice to store data that will be heavily reused. Note that for Zenodo, there's no check on the data quality, so you can put anything and nobody's gonna say, see whether or not the data is usable. These other ones, Pangea, I'm a little bit less familiar with, but I think it also comes with nice services for creating data set. Figshare is another one where you can get, I think I've seen it a couple of times using for a smaller data, but it's also kind of free. Not kind of, I think it is free. So these are nice platforms where when you submit a paper and a code associated with it, you don't even have to clean up your code. You can just say, when I submit my paper, I will submit all the scripts that I used and maybe the data products, if not the raw data, onto these platforms. And then you attach it to your paper. So then the reviewers and the readers will be able to access all of your work. Now let's talk about this famous paper you probably have heard about, FAIR principles for open data. So this is a paper from geoscientists. It was a Wilkinson et al. 2016 that designed principles for what FAIR data stands for. And this is a good model to follow when you want to package your data products. So data has to be findable, accessible, interoperable, and reusable. And to adhere to these principles, you have to follow things like, the data and the metadata. They need to be findable, so they need to have an address, persistent identifier that's unique and findable by others. So that's the piece of the DOI. Data is described with rich metadata. Data is clearly and explicitly included in the identifier of the data, and so on and so forth. Accessible, you need to make it available in an open protocol, so that's what Zenodo would do. Universally implementable. Interoperable is interesting, and we'll talk more about this for the software bit. But this is saying that the data should be a formal, accessible, shared formats, and that can be used among different, applicable with different languages, so C and Python and readable with all of that. And reusable is the idea that if you create a data product that has like a database with columns, for instance, and you do not put headers or column heads, so you read your Panda data frame and you don't even know what the columns are. The idea is like, if we want people to reuse it, make sure that the metadata is rich enough for people to be able to do interpret it and do other things with it. So we have just talked about this general repository archive. We have the really domain-specific archive. So we have Earthscope. There are services that host all the data that you may have collected through Pascal, or there might be some European equivalent of the raw data being hosted by these data services. These are really nationally supported archives, the gold standard for following the guidelines for FAIR. Everything is licensable, citable. All the networks have DOIs. You can also put all this less structured data in Zenodo, fixed, dried, or not. It is citable, but it's a little bit less integrated, less curated, but it's just kind of like your bucket full of data you want to put out. And then sometimes you may also put your data in some of these journals. So there's data-specific journals like Earth System Science Data. Seismology is doing one of them, and I have a few on the list later on. And you can find actually a registry of all of these in Registry of Research Data Repository. So on this website, it's kind of a nice searchable database of all kind of archives. I think some of these are listed, most of them are listed in this repository. So anyway, there's a lot of data out there that you can go through. AGU is now requiring data access and code access. So data access, it must be repository in something that supports FAIR. I think Zenodo, which does not have this guarantee of fairness, works as well. You need to show a data availability statement. So that comes with data citation. For instance, you should use the DOI of each network that you have used. And the reason is, just simple. It's not just a respect for the seismic network or the people who deploy these stations, but it's actually the one way that this seismic network, for instance, will track their data usage. And if they have well-used data, then they can actually talk to the NSF and say, hey, we use, our data is used, please keep funding us. So part of this documentation on citation is really important for these operation to work and justify the data collection. And maybe we take things for granted because IRIS has been delivering data in my generation for free always, but they have to always justify to the funders the reason why. And so citing the data is one way to get them a little plus on the counts of data users. So please start doing that or continue doing so if you can. This is just a simple state of acknowledgement in the data availability statement. When you cite a paper, something that it will become mandatory at some point is please try to follow standards, including having the DOI in it. It is so annoying that Google Scholars will not put the DOI link. It would be so much easier. They have a big tech integrated copy paste from Google Scholar, but they don't put the DOI. But it is super important thinking about what is the DOI. That's the persistent identifier of this data set or paper, and then maybe when you're accessing the last time the archive. Anyway, a bit more on where to store the data. Just want to say we have some national archives for that are domain-specific science, so IRIS and UNEFCO join, maybe the USGS as a database. Computing centers may or may not be able to host data, so that depends on institutions. Maybe Ian will talk about this more later on. Institutional have maybe their own repository. At UW, it's called ResearchWorks, but as a seismologist, I'm like laughing because they allow up to a few gigs of data, so it definitely doesn't work for us. And then of course we have the other general repositories. Okay, so some brief talking about how some journals will require open data, but will not be open access. So for instance, most of Nature papers require materials data codes to be and associated protocols to be available to the reader without undue qualification, which means contact the author to get the data, for instance. AAAS journals, yes, the nonprofits still recommends that generally require that the underlying data is publicly immediately available. You cannot have contact the author for accessing the data, and they also recommend that it meets the community standards in machine readable format, which is basically what I just talked about. So these kind of high-end journals do recommend open data, even though they're not open access. Okay, so we have other open access journals that you can publish your data. Geoscience Data Journal, Scientific Data, Earth System Science Journal, Seismological Society of America has the SR Data Mine that you can go with it. If you know others, basically, we are going to talk a little bit about Seismica and the other series of journals that are fully open access in a little bit when Alice turns us back. So now I want to switch to open notebooks. And open notebooks is a little bit more of that description of the workflow that you use. And so this is pulled out of the Jupyter project from Berkeley. And what is, well, most of you worked with notebooks, but what's nice about let's basically break down the components of what the notebook is. The notebook is a stack of modular and open tools. It's a package ecosystem. So you have a Python or a package that comes with it. It's a document with a standard data format. This is a, I think, JSON file for IPython notebook. It may have a server protocol. So you may have a back-end server like a Collab or a Binder or others. It may have interactive kernels to go along with it. And then by the end of the day, you publish your awesome report. And so the full stack of the notebook is the full stack of these. And so I like this little introduction of why we should promote the development of notebooks for our research. This is an example that Jane has written a paper based on her experiment, and she'd like anyone to be able to reproduce, check, and improve on her calculation. What a good model, right? Don't we all want that? So step one, she described her experiments in a notebook. She makes this pose code visualization, and that resource has the source data, the data, the metadata, the media, and so on. Then she publishes them in a publicly hosted repository, which might be GitHub, Bitbucket, GitLab. And then she might actually have a way to link this notebook to a backend server like Binder. So with a nice configuration file, we should be able to have a Binder ready deployment of our notebook. So we can actually, everybody should be able to also have free cyber infrastructure to reproduce the work. And from there, it's distributed and everybody should be able to reproduce the workflow. So I want to conclude on this. Actually, I didn't check the time. So Alice and Dave, you should interrupt me when it's time. But really the checklist that I'm trying to promote in my group and others is share, publish, and archive. Share your information, how you process your information, your data, and things like that. Publish the raw data, the metadata, the data products, and archive for the long term. So for code and data, think about citable DOIs and findable using these nice platforms. Anyway, I might stop here. Alice, would you mind commenting if I don't try the time? I can get on and on these things.
I think we're good in time. I mean, for
Okay.
my part, I might need 5 minutes or so. So if you want to continue through the material for another 5 to 10 minutes, I think we're still fine. I
will check the time this time. Okay. I wanted to talk to you a little bit about this, the FAIR principles for the data. And so while we don't have to go this table and details, I just wanted to point out this is already 5 or 6 years old now, and they already had laid out some things that are still not fully adopted by everybody. And so you may want to look at what their vision of what the papers for the future was about. A modern paper will have narrative of the methods, some data maybe in tables, figures, and plots, in software that is used. The data is included in the supplementary material or pointed to from data repositories. If it adheres to reproducible publication, which we're not there yet, we need the software, data preparation, data analysis, and visualization to be available. We need to also talk about provenance and methods, workflows, and all the scripts for the data flow, all the codes, the configuration files, and everything. All of that should be packaged and demonstrated for, or ideally, demonstrated for the publication. On this piece, there's a checklist that they recommended. This came out of a couple of workshops, I think, about what to do to prepare a kind of a paper, a work that follows open science. And so I broke it down in a couple of pieces here. They talked about the data itself, data accessibility, choose a general repository, create a public entry for your data, specify your metadata, upload the data, and so on. Accessibility, find the repository for your community. So figure out, like, my community use Zenodo, I will use Zenodo. If others use Dryad, then think about using Dryad so your colleagues can access it easily. Data documentation, really enrich your metadata information so then it can be reused. And what to show in the paper, you may want to cite the data set and the papers that are associated with that. The citation should be standard. And yeah, so some of that recommendations. Software, we'll talk more about software in a follow-up session, but in their vision of what a solid paper should be like, the software should be accessible. The simplest approach would be a public entry for the software. So if you put and double your files on GitHub, just link your GitHub for that. You could also get a DOI for this. Just specify very basic metadata about this, choose a license, and provide some kind of citation for that. So that's the simplest approach. If you want to have more advanced way, curate your GitHub or big buckets to allow version tracking, things like that. Be more specific maybe about the license that you may want to use depending on the software that you have used before. Think about putting maybe your GitHub into a software registry so it's even more visible to the community. And be mindful of the data formats that you may use. HTML, XML, all of the metadata in data formats should be standard. When you cite a software in your paper, that's always good to support the software development team, and maybe funding further the development. So please be mindful of also citing the software and the papers that were attached to it. And then computational methods. So this is a little bit, so we had the scripting part, the data part. The workflow is particularly complicated for data mining projects. So they also recommend that we can be specific in the text or in the script about what workflow we're doing. So the simplest approach will be you have a trace log of all the computational steps. You may provide a summary text in the paper, in the text, or in some external text with data, software, specify the versions and everything that you've used, and then maybe you have a workflow diagram of data ingestion, data processing, and so on. And then you can go, of course, and do more steps toward more advanced way of documenting your workflow. But just know that even the simple steps are already a good step forward. When you publish, another things that will be that will help promote open science is to consider the contributions of all the authors that you've worked with and the co-authors of your paper. And one thing that I think journals are moving toward is finding a nice lexicon about the types of activities that are engaged during a research investigation, what gets to be associated with authorship. So here are the credits. Taxonomy. I actually use that always in my papers right now, so it makes it very clear, standard, and also just not complicated with authors. If you say what part of the paper did you contribute to, software, supervision, editing the paper at the end, anything that has contributed to the paper is also one way to acknowledge the community and your collaborators in the publication. More details on this. Now, in transition to what Alice will talk about is discussing this open access crisis, which lead the way to a shift in the way our community is engaging in publication. There was this nice little comment in Vox in 2019 about what happened at the UC system when UC says no to some of these very expensive subscription. And so they showed a nice chart about expenditures on as a time series for how much people and institutions are paying on for this subscription in journal. And you can see that a regular inflation index would be from 1986 until 2014, 100% increase. This is tracking inflation and cost. The total expenditures of these journals on publishing has gone about twice that rate, almost 200% in this span of time. But what they are charging the institutions and others is way beyond what they're actually spending. Excuse me. And so, so UC was at some point just said no to Elsevier that was charging $11 million for accessing papers. And so this has really exploded, I think, for us in thinking publicly funded research. We write for free for these journals. We have templates that we have to follow so they don't have to typeset. And then you still have to pay to read your own paper. It's kind of crazy. And so this has really shaken up our community to reconsidering the way we publish. And so there's different levels of open access that you've noticed in some of these papers. And AGU is, I think, kind of moving in the right direction. I say nature is for profit. Nature communication is open access if you pay for it. The fees for these are, 6 months of grad student salary in the US, probably 1 year in Europe. I won't comment more on that. Science magazine, it's nonprofit. Science Analysis is open access, but there's still a lot of fees that goes with accessing the science journal for in general. Another thing that I found myself kind of disappointing when I review papers, for instance, is sometimes disconnections between the editorial board and the actual scientific community. So in general, I actually avoid writing to these journals. So I really like actually working with AGU, as a good go-to for a lot of these journals. Many of them have open access. So go to open access. You can see the diagram here that shows the different levels of accesses. So it's free for authors. It gets peer reviewed. It's free for reader, and the authors maintain the copyrights. And you can see that there's different combinations of them. So the free for reader I really care about, because for publicly funded research, might as well have the public see what they're funding. And so you can see the intersection of these. So free for readers and free for authors to publish. Then we have maybe green open access. Free for readers, we have these preprints archives. And you can see the intersection. And then Alice is going to talk about what this really the synergy is when you actually have everything free for everybody using Diamond open access. So maybe it's a nice time to transition.
Sure.
Would you like to screen share, or do you want me to just click next?
If you want, you can just click next, actually. Might be the easiest. Okay, so I will try. Hello, everyone, again. I'm one of the co-organizers, Alice Gabriel, and I will talk a little bit about one example for Diamond open access publishing in seismology, and that is Seismica. So Seismica is a new journal that was driven by the community and has been invented by the community. And I was a member of the task force that came up with the idea that we in seismology need a diamond open access journal. So what is Seismica? As I said, it's community-driven, open access. We do have peer review. So I just got this question yesterday again at some SCAC leadership retreat. If there's no peer reviews, there is peer reviews, but it is free to publish and free to read. So if your paper is accepted and it is published, you don't have to pay anything. And if you want to read Seismica's publications, you also don't have to pay anything. And this is what the Diamond Open Access means. We publish research articles, reports, so fast reports that will be processed within 4 weeks. We also had this idea about publishing null results. So null result is if you try something and it really doesn't work out. And often these kind of insights are not being published, but we are able to publish this because it is actually beneficial for our field. Instrument deployment, field campaign reports, software reports, important in the context of our training, opinion articles and reviews. And we are accepting articles. There's around 16 papers published so far. I think we have at the moment 60 in our system that are being reviewed or being revised and so on. And we also reject papers. So, it's just operating like a normal journal. So next slide, please. How Seismica organized. This is especially interesting because we're always looking for new people that are willing to join. We have a board, which is quite a large group of people that consists of handling editors. So these are people that are, receiving your paper and are finding reviewers for your paper. There's also more roles than maybe in traditional journals, that are, for example, just looking into equity, diversity, and inclusion aspects, or that are only looking into, making sure that not only the paper, but also the, for example, the code statements and the software is reproducible. And it's a global endeavor. So next slide, please. Why? Well, you can read through that. We believe it's important for the community to have this Diamond Open Access kind of playground of how publishing could look like, without all the aspects that Marine just talked about. We also have, since it's a small and community-driven journal, we have a lot of flexibility to try new things. So one of the example is that we're having abstracts in 2 languages. So if you're studying the Turkish earthquakes, we can have abstracts in Arabic and in Turkish to directly, directly talk to people in Syria and Turkey. That's just one example. Next slide, please. The journal scope. So we're trying to cover all of earthquake science. We're also interested in community engagement, communication and outreach, engineering seismology, techniques and instrumentation, theoretical computational seismology, which is very dear to my heart, earthquake records, imaging, fault slip and earthquake source phenomena. Next slide, please. We have author guidelines that we spend a lot of time on developing. So you can see them here summarized here. Important data and code, really aligned with what you just heard about. All data and codes should be freely available wherever possible. Data availability statements are required. You can also choose to be reviewed in a double anonymous way. So that means you can hide your identity as an author. So you can avoid any bias that might be related to releasing the name of the author team. Next slide. These are just a few of the articles that we've published so far. A recent one by it's one of the first papers about the Turkey-Syria earthquake sequence. We're also thinking about glacier seismology, and there's something about imaging. So these are just some of the examples. Next slide, please. So how to be involved? You can submit a manuscript. You can sign up in our reviewer database. So this is important. Established journals have huge databases of reviewers, so people that are willing to review, sorted by subject and sorted by expertise. So we have this self-organized database where members of our community are signing up if they're willing to dedicate their time, to a completely open journal and help us reviewing papers. You can get publication notifications, you can interact on social media, and you can really join our team in several roles. We have a lot of early career researchers that are helping us with typesetting, for example, and with more technical aspects. And it's a good way to be trained to take on more higher responsibility roles in the world of publications. Next slide. I think it's the last slide. Yes, if you're interested, we don't have time to play this video, but this is a recording of a talk by Christy Rowe, where she's really highlighting why Seismica is a tectonic shift in the publication world in seismology. So that was a talk she gave at the SCAC meeting, I think, last year. So I encourage you to watch this. It's she summarizes it much better than me, and it's a good watch. And with this, I stop.